In this chapter, we are exploring single variable linear equations. Today, we will focus specifically on section 2.2, manipulating equations, and section 2.3, more equations. Let's master these core concepts together. An equation states that two expressions have the same value. The expression on the left is the left-hand side, and the expression on the right is the right-hand side. When variables are included, the value that satisfies the equation is called the solution. Think of an equation as a perfectly balanced scale. The equal sign represents the center pivot. To keep the scale perfectly horizontal and balanced, the mathematical weights on both sides must always be exactly identical. To solve equations, we use the properties of equality. The addition property states that if A equals B, then adding C to both sides maintains the equality. Similarly, the subtraction property states that subtracting C from both sides gives an equivalent equation. These operations allow us to isolate the variable and solve the equation. Let's visualize this with a simple scale. Imagine two identical mystery boxes that have the exact same weight. If we add the same amount of sweet candy to both sides at the same time, the scale remains perfectly horizontal. Even if we take away the same number of candies later, the perfect balance never breaks. Let's test our understanding with a practice problem. Solve the equation x minus 6 equals 13. To isolate the variable x, we apply the addition property of equality. By adding 6 to both sides of the equals sign, the balance is perfectly kept, and we successfully find that our solution is x equals 19. Next, we have the multiplication and division properties of equality. The multiplication property states that multiplying both sides of an equation by the same number C keeps the equation balanced. Similarly, the division property states that you can divide both sides by any non-zero number C. Just like addition and subtraction, these operations help you isolate the variable perfectly. Let's check the multiplication and division property with shapes. Here is a balanced scale with one mystery box on each side. If we multiply the left side by 2, we double the number of boxes. To keep the scale perfectly level, we must also double the right side instantly. The same rule applies when dividing. Cutting both sides exactly in half maintains the balance. Let's test what we have learned with another practice problem. Solve the equation 4x equals 32. To completely isolate the variable x, we must use the division property of equality. By dividing both sides of the equation by 4 at the same time, the perfect level balance is kept. Simplifying this calculation leads us to our final answer, x equals 8. To solve equations with fractional coefficients, we can clear the fractions to make things easier. We do this by multiplying both sides of the equation by a common multiple of the denominators. The most efficient number to multiply by is the least common multiple, or LCM. Let's look at this equation with denominators 3 and 5. By finding their LCM, which is 15, we can transform this into a much simpler integer equation. Let's visualize clearing fractions using cake slices. Dealing with sliced pieces of cake on a scale can be complicated. However, if we use a magic number to multiply the slices on both sides, those broken pieces instantly combine into beautiful whole cakes. Multiplying by the least common multiple changes messy fractions into clean integers. Let's test our skills with a comprehensive problem. Solve the equation 1/3 x minus 2 equals 1/5 x. To clear the denominators 3 and 5, we multiply every single term by their LCM, which is 15. This converts the equation into 5x minus 30 equals 3x. By rearranging the terms step by step, we get 2x equals 30. Finally, dividing by 2 leads us to the answer, x equals 15. Let's solve a similar advanced problem together. Consider the equation x minus 1 over 3 minus x minus 2 over 4 equals 5 over 12. We have 3 different denominators, 3, 4, and 12. Their least common multiple is 12. By multiplying every single term by 12, we can perfectly clear the fractional coefficients. This leaves us with 4 times the quantity x minus 1 minus 3 times the quantity x minus 2 equals 5. After opening the brackets carefully using the distributive property, we group the terms step by step and successfully find that our final answer is x equals 3. When an equation contains decimals, we can clear them by multiplying a power of 10. Let's look at this equation. The numbers have up to 2 decimal places, which means hundredths. Therefore, we multiply both sides of the equation by 100. By doing this, every single decimal term is converted into clean integers. Then we rearrange the terms, group the variables, and solve it cleanly without any fractions. Let's tackle a similar advanced problem involving thousandths. Solve the equation 0.012x equals 0.3 minus 0.018x. Since the numbers contain up to 3 decimal places, we multiply both sides by 1,000 this time. This step clears the decimals, yielding the integer equation 15x equals 300 minus 25x. Next, we move the variable term by adding 25x to both sides, which simplifies perfectly to 40x equals 300. Finally, dividing both sides by 40 brings us to the verified solution, x equals 10. Let's learn how to translate real-life word problems into equations. Consider this task. The sum of 3 times a number y and 5 is 26. First, we identify our variable, which is already labeled as y. Next, we write out the given information as an algebraic equation, yielding 3y plus 5 equals 26. To solve it, we isolate the variable term by subtracting 5 from both sides, which gives 3y equals 21. Finally, dividing both sides by 3 brings us to the final solution, y equals 7. Let's explore sequences with a common difference. Consecutive even integers always increase by a fixed amount of 2. Imagine we need to find 3 consecutive even integers whose sum is exactly 72. We can visually represent them as x, x plus 2, and x plus 4. Adding them together gives the equation x plus 2 plus x plus 4 equals 72. By combining the like terms, this simplifies beautifully to 3x plus 6 equals 72. Subtracting 6 from both sides gives 3x equals 66. Finally, dividing by 3 shows that the first integer x equals 22. So, our 3 consecutive even integers are 22, 24, and 26. Speed, time, and distance are all connected by a simple mathematical relationship. Speed is defined as the distance traveled per unit of time. We can visually arrange these variables into a formula triangle. Distance stays on top, while speed and time occupy the bottom positions. By rearranging this triangle, we discover that distance equals speed multiplied by time. Let's test this concept with a practical practice problem. A train travels at a steady speed of 65 miles per hour for exactly 4 hours. To calculate the total distance covered, we multiply the speed of 65 by the time of 4. This gives us the final equation. 65 times 4 equals 260. Therefore, the verified total distance is 260 miles. An absolute value represents the distance from 0 on a number line. When an absolute value contains multiple terms, we must keep them together. Let's solve the equation. The absolute value of 3x minus 4 equals 8. This means the expression inside 3x minus 4 can be either positive 8 or negative 8. We split this into 2 separate cases to solve. For the first case, 3x minus 4 equals 8. Adding 4 gives 3x equals 12, so x equals 4. For the second case, 3x minus 4 equals negative 8. Adding 4 gives 3x equals negative 4, which simplifies to x equals negative 4/3. Both answers are verified and correct solutions.